Deep in space, stars burn like giant fires. Deep inside their cores, hydrogen releases enormous amounts of energy. That energy pushes outward, while gravity constantly pulls inward. As long as those two forces stay in balance, the star survives. But what happens when the fuel runs out? Gravity finally takes over, crushing the core harder and harder. Then comes one of the most powerful explosions in the universe. A supernova. The outer layers of the star are blasted into space, but the core remains. Gravity keeps crushing it until electrons are forced into protons. They merge together and become neutrons. The atoms we know disappear. This is how a neutron star is born. Something once millions of miles across is crushed down to a sphere only about 12 miles wide. If you could somehow hold a single teaspoon of neutron star material, it would weigh around 1 billion tons. At that density, it should keep shrinking into a black hole. But it doesn't. Even today, scientists still don't fully understand what lies at the very center of a neutron star. What they do know is that during its first 10 seconds, the newborn star releases almost 10% of its mass as a flood of neutrinos, ghostly particles racing through the universe at nearly the speed of light. Against all expectations, what should have become a black hole becomes something even stranger. But this is only the beginning. How can something heavier than the sun spin hundreds of times every second without flying apart? Imagine a figure skater spinning with their arms stretched out. As they pull their arms in, they begin to spin much faster. Not because they're pushing harder, but because the same motion is now happening in a much smaller space. The same thing happens when a massive star collapses. Its mass barely changes. Imagine taking the entire Earth and compressing it until it fits inside a coffee mug. Nothing disappears. Every mountain, every ocean, and every continent is still there, just squeezed into a space millions of times smaller. The star undergoes the same kind of collapse. As it shrinks, its rotation speeds up dramatically. Some neutron stars emit narrow beams of radiation from their magnetic poles. As they spin, those beams sweep across the cosmos like a lighthouse beam. Most of the time, they never point toward us. But when one briefly sweeps across Earth, our telescopes detect a flash of radiation. To us, the star appears to blink. Astronomers call these objects pulsars. They spin so fast that they almost seem impossible. The fastest one ever discovered completes 716 rotations every second. By the time you've blinked once, it has already spun more than 200 times. Its pulses are so incredibly precise that astronomers use them as natural cosmic clocks. Some rival the best atomic clocks on Earth. Its surface races at nearly 1/4 of the speed of light. Any faster, and the star could tear itself apart. But even that isn't the most extraordinary thing about neutron stars. If spinning sounds impossible, what comes next is even harder to believe. Some neutron stars are born with magnetic fields so powerful that they become something entirely different. These are magnetars. Why some neutron stars become magnetars while others don't remains one of astronomy's greatest mysteries. To understand just how extreme they are, we need to start much closer to home. Earth has a magnetic field too. You can't see it, you can't feel it, but it quietly protects everything alive on this planet. It acts like an invisible shield, deflecting charged particles from the sun. Without it, Earth's atmosphere would slowly be stripped away, leaving the surface exposed to deadly radiation. Now imagine that same invisible force, only 1 trillion times stronger. That's the power of a magnetar. If you were somehow standing about 600 miles from a magnetar, its magnetic field would be powerful enough to tear apart the atoms in your body. Not your cells, not your DNA, the atoms themselves. And we still don't know exactly how nature creates a magnetic field this powerful. For decades, magnetars seemed too distant to ever affect us, until one night in 2004. A magnetar known as SGR 1806, nearly 50,000 light-years away, unleashed the most powerful burst of energy ever detected from outside the solar system. In less than a second, it released more energy than our sun produces over hundreds of thousands of years. The flash was so powerful that it overwhelmed space telescopes and gamma-ray detectors, leaving many unable to measure its true intensity. Yet even from the other side of the Milky Way, its radiation was powerful enough to ionize part of Earth's upper atmosphere. But what if it had happened much closer? A burst like this wouldn't have to destroy Earth. Instead, it could quietly erase something almost every living creature depends on: Earth's ozone layer. Yet this radiation explosion isn't the only threat to Earth. The sun is. The same star that gave Earth life could suddenly become the force destroying it. And this may not be just a hypothetical scenario. Around 440 million years ago, Earth experienced one of the most devastating mass extinctions in its history. Nearly 85% of marine species disappeared. One hypothesis suggests the trigger may not have come from Earth at all. It may have arrived as a burst of gamma rays from a distant magnetar. If that's what happened, then the history of life on Earth may have been rewritten by an explosion that happened on the other side of our galaxy. Our galaxy may hide 1 billion neutron stars, yet we've found only a few thousand. The rest drift unseen. Some no longer emit radio waves. Others simply never point their beams toward Earth. They remain almost impossible to detect, which means we still know surprisingly little about our own galaxy. Some of its most extraordinary objects may still be out there, completely unseen, drifting silently through the darkness.